around the star. Remember, all these methods are indirect methods. We are not directly looking at the planet, but we are looking at the star and I'm measuring the stellar properties, whether it's motion or its transition, its brightness. We are indirectly getting information about the planets. And in astronomy, we usually don't get direct information. I usually, tell students that astronomy is not very straightforward. No science is, no research is straightforward, but astrophysics is even tricky business, because here we don't have any control over our experiments. We cannot change the parameters. We cannot change the setup. We cannot design our own setups. The nature has given a well-established laboratory called universe. We are just observing the objects, and that too using only light. So just analyzing light coming from the further objects and getting information about this system. So indirect evidences are very crucial in case of astrophysics. But there are some exceptions. In some cases, we can actually detect planets directly, and I'm going to show some beautiful examples. See, the reason we cannot see these planets directly, as I explained, the brightness of the star is the real problem. If you compare the brightness of the planet and the star, the planet is most of the time millionth time fainter than the star. Very, very faint. So star, overshines the planet. But like solar eclipse, if we arrange something within our telescope such that we can eclipse the star itself, exactly the star, not its surrounding space. If we can arrange something, you can put some obstacle in the light path at proper place in our telescope, we can actually occult, we can actually eclipse our star, and in that condition, we can see the planets, faint planets around the star. So two examples I am showing here. The glow around this square shape is actually glow from the star. But this square shape is actually the obstacle I have kept in my telescope. Actually, not I have kept, the other scientists have kept in his telescope, such that it blocks the starlight. And when you block the starlight, you can see the surrounding space. And there you can see two objects, this bright planet and this reasonably faint planet. The other, even convincing example is this. When you occult the star, even still, you will get some fraction of the light from the star. So this central globule is actually leaked light from the star, but that leaked light is millionth time of the total starlight. And when you have reduced the starlight, you can see three bright, clear dots. One dot is very close to the star, the other is at intermediate distance, and the third one is at farthest. These three dots are basically three planets. So these three planets are orbiting around the star, and we have actually directly imaged this. So these two pictures are real pictures. Many of my presentations pictures are artist imaginations, but whenever I will show the real picture, I will explicitly mention it. And the other real picture. This is even interesting. This is actually newly born star. A star usually borns from a disk, accreting disk. So when you hide the star using this circular obstacle, you can see even the disk-like structure also. Like this two jet-like structure is actually a circular disk, but you cannot see the disk as a ring because you are seeing the disk from the edge. So you can see this as a line. So this star is called Beta Pictoris. It is a variable star, and if you hide its light, you can see there is a bright spot around that star. And this is called Beta Pictoris B. The main star is called A, and rest of the planets are called B, C, D, E, F, G, H, and so on and so on. So this is the first planet, so it is called Beta Pictoris B. More convincing example. And here you'll see that the same star, Beta Pictoris, have been observed in near infrared wavelengths for more than once. It was observed in 2003, and you could see a planet here. When the star was observed again after 6 years in 2009, we can see the planet has moved from point where it was in 2003 to almost opposite point in its orbit. So you can compare, the planet has revolved. So actually we have not detected the planet, we have detected the motion of the planet around the star. And here the orbit of the planet is compared with the Saturn's orbit. The orbit is much smaller than Saturn's orbit. It is larger than Jupiter's orbit, but smaller than Saturn's orbit. So we have convincing evidences that yes, we have detected planets, whether directly or indirectly. And now with development of technologies, we have not only detected planets, we have detected spectra. We have obtained spectra of the planet, or the spectra of the atmosphere of the planet. See what happens. Suppose you are observing a transiting planet. When planet is not in transit, the spectra you are getting is purely from the star. But when planet is transiting, the planet is between the observer and the star, some of the starlight will pass through the atmosphere of the planet and will reach to the observer. You again take a spectrum. Now you have two spectra. One spectrum from the star itself. The other spectrum is the star plus planetary atmosphere. When you subtract these two spectra, the stellar spectrum will be subtracted, and what you will get will be purely the spectrum of the atmosphere of the planet. However, it is not easy to get a signal in the spectrum, I mean spectrum with good signal in this case, because when you subtract it, what remains is well below the error bar of the spectrum itself. So we have to apply a lot of computational and observational techniques to reduce the error bars, and then we get spectrum like this. So this is a real spectrum of a particular exoplanet, and there you can see that you have detected three bumps, three emission-like structure in the spectra. The black dots are actual observed spectra, whereas these red and blue lines are the model spectra fitted in this observed spectrum. And there you can say that, okay, the atmosphere of this particular planet contains H2O, most likely in vapor phase. So this way, analyzing this planetary spectra, you can confidently say about the composition of their atmosphere also. And this is a big thing. Sitting here on the Earth, you are talking about the planet revolving around a bright star. The star is hundreds of light years away from us, and still you are talking confidently about their atmosphere and their composition of atmosphere. With this, I will come to some very interesting examples of exoplanets. The exoplanets are, in varieties. We have discovered thousands of exoplanets, and many of them are totally unique, weird, diverse in their nature, in their characteristic, in their properties, and it's difficult to explain all these exoplanets. So I have selected some examples. One of them is called Kepler-11 system. This is actually a planetary system where more than one planet, around 5 planets are orbiting around a single star. The uniqueness of this system is all these 5 planets are very close to their host star. This is very compact system. So all these 5 planets are actually settled, their orbits are settled within the orbit size of Mercury. So they are very close to the star. So this example shows that the multiple small planet system, like our own solar system, is very much common. Sun is again, solar system is again not a special system. It is a common system in the universe. Other example, other unique system is called Kepler-16b. So this planet is orbiting not around a single star, but interestingly around a binary star. So in universe, we have discovered that 90% of the stars are not alone. They are, clubbed with one or more stars. So they are forming stellar system. Sun is falling in that exceptional 10% range. Sun has no binary component. Most of the 90% stars are binary in the system. So 2 or more stars are orbiting around their common center of mass. This Kepler-16b, this planet is orbiting around such binary system. Very unique. So this planet is orbiting around the circumbinary space. Other example is HATP 7b. See, this is a very interesting and very unique system. When we studied the atmosphere of this transiting planet, we discovered that the atmosphere is very rich in aluminum oxide. This is corundum. And we know that the crystal structure, the corundum, rubies and sapphires are actually the crystalline forms of the corundum. The atmosphere is rich in corundum, and this atmosphere highly dense, and conditions are such that scientists, astrophysicists have guessed that probably in their atmosphere, rubies and sapphires are raining like anything. Unfortunately, they are very common on those planets. So if some alien organisms are living on that planet, they don't have value of these rubies and sapphires. Other interesting example is 55 Canceri E. This E represents that this 55 Canceri has more than one planet, B, C, D, E, at least 4 planets. Actually, this system has 5 planets. I'm talking about the 4th one. This is actually a diamond planet. We know that the atmosphere of this planet is rich in carbon and also under extreme pressure. So we are very confident that this planet is rich in diamonds. Diamonds are spreaded like, stones, rocks on the earth. So though diamonds are rare, they are not rare everywhere in the universe. Also, this is interesting to know that this planet is very close to its star. It orbits around its star barely in 18 hours. Much faster than the closest planet, Mercury, also in our solar system. So this poses a challenge to theoretical astrophysicists. Earlier, people believed that no planet can form such close to the star. The stellar gravitation can destroy the planet before it forms. But then we discovered this planet, and theoretical astrophysicists had to reform their theories. Another interesting example is this PSR, this number system. I will not read it. This planet, the planet you can see here, is orbiting not around an ordinary star, but orbiting around a dead remnant of a dead massive star. This is called neutron star, or rather a special neutron star called pulsar. So this pulsar, pulsating star, hosting a planet, a very unique system, and this planet shows us that the planets can exist anywhere, even in the harshest conditions of this highly magnetic pulsars also. And this is also probably the smallest planet known till date outside our solar system. Another example is not about planet, but structure around the planet. So JA1407b, this planet is actually hosting rings ring-like structure, very similar to our Saturn structure, but the ring-like structure is extended to enormous size, and that's why this planet is, called Saturn on steroid. See, if we put this system at the place of Saturn, see, we cannot see with bare naked eye the rings of the Saturn. But if we put this system at the place of the system, the rings of this planet covers area much, much larger than the size of the moon itself. So this system is comprising very big ring-like structure. And we have discovered that the largest ring is probably 650 times larger than the Saturn. Though we have discovered thousands of planets, I should mention that we have not explored full universe. We have not explored our own galaxy also. We have explored a small circle of barely few hundred light year region of our galaxy. There are millions of stars in this circle, and we have detected planets around this small circle only. Imagine if there are thousands of planets in this smaller region, with all this weird nature, what can we say about all the planets in our galaxy and about such billions of galaxies? So universe is full of surprises, full of secrets. It's up to us to explore, to pursue, to discover these secrets. With this, I will enter the right slide of my presentation, this topic. And see, not all planets are comfortable to live with. Like in our solar system, the planets, Mercury, Venus, Jupiter, or other planets are either too close to sun or too far to the sun, such that the water cannot exist in liquid form. So depending on the temperature of the host star, there is a specific distance range within which if planet exists, then the planet can host water in liquid form. So this region is called habitable zone. And we have discovered several planets in their habitable zone also. So we have good hope that someday we will discover planet very much like Earth, where life can exist or life might have existed. We will discover that, but apparently it is not possible in near future. With this, I will quickly move to my second topic, and that is another extreme. The exoplanets are substellar bodies. Now I'm talking about black hole, which are, I would say, superstellar bodies because of its heavy gravitation. So though black holes are fascinating and elusive till date, the concept of black hole is not very old. In 18th century, non-mathematician Laplace has suggested in his book that high gravity objects may trap all the radiation emitted by itself. And he has clearly written that it is therefore possible that the largest luminous bodies may, through its course, may be invisible. So in universe, usually the larger the body, brighter it is. But in this case, if the body is large enough such that it has gravitation to hold all its radiation, we cannot see it. It is invisible. So this concept is nonsense long, but again, the matter of discovery. Carl Schwarzschild has mentioned in his paper, in his letter to Albert Einstein, and explained the theoretical possibility of an object holding all its gravitation. But Einstein was suspicious about the actual physical existence of such object. Schwarzschild has calculated the radius of such bodies with respect to its mass. So, on Earth, we know that the escape velocity is 11.6 kilometer per second. That means if something is thrown higher than this velocity, it can escape from Earth's gravitation. Actually, it cannot escape from the Earth's gravitation. There is no boundary of Earth's gravitation, but we can think like that, that the object is moving away and away from the Earth, and as it is moving away from the Earth's gravitation also become weaker. And that way, gravitation has no hold to bring that object back on its surface. So this escape velocity is key part here. The escape velocity is function of mass of the body as well as function of the radius of the body. If you hold the mass of the Earth as it is and you reduce its radius, you are actually reducing the distance from the center, and that way you are increasing escape velocity. So escape velocity will increase. If you keep shrinking the object, say Earth, you can make the Earth of such tiny ball such that the escape velocity of Earth's surface, new surface, is more than 300,000 kilometers per second, and that is the speed of light. In this condition, even light cannot escape from this shrunk Earth, and so Earth becomes black hole. Interestingly, Schwarzschild has a meaning in German language called black shield. So Schwarzschild is actually making his name worth. उन्होंने अपना नाम यथार्थ किया. You know, some examples of the hypothetical radii of object if we want to make them black hole. So if you want to make Earth as a black hole, you have to shrink it to 1 centimeter radius. Very tiny ball. In case of sun, it is barely 3 kilometers. And if you have a star more than 3 solar mass, the size of that black hole, made from that star is 9 kilometers. To an extreme, if you have an object 1 billion solar mass, then you can shrink this object to make a black hole, and still the size of the black hole is 20 astronomical unit, that is comparable to Jupiter's orbit. So if this object has sufficient mass, even the black hole of this object, black hole made from that object, is large enough. So black holes are not only tiny objects. You can see here that when we shrink the object, the dent it made in the space-time structure goes deeper and deeper, and eventually it will reach a level below that you can't see. Whatever happens here below this limit, you can't see. The information cannot reach to you standing in outer universe, and that's why this limit is called event horizon. So this is the horizon below which we cannot see. Any event we cannot see below this horizon. So the black holes are actually patch in the universe. It's a spot, or it's a hole in the universe. Here you have a space-time structure, and you can see that even from ordinary star, the light feels the effect of gravity. As light moves away from the star, first of all, it loses the energy, and that's why it is keep changing its wavelength also. So as light moves away from the star, massive star, it becomes redder. This is called gravity reddening. But if the star is actually a black hole, and if you throw a light beam at a proper angle, the light cannot escape from the star, but actually this light beam orbits around this black hole. And these photons are actually like a satellite, they are orbiting around this black hole. So for a given black hole, you have an angle beyond which light can escape, but below that angle, the light can trap within that black hole. So either light can fall back to the black hole, or it can orbit around the black hole. So this is very interesting to know that all the black hole has a photon sphere. Photon sphere. So photon sphere is a sphere around the black hole within which the photons are bound to orbit around the black hole. They can neither escape away in the space, nor escape, nor fall towards the black hole. Very interesting fact. A secret. How these black holes form? I think I don't have much time, so I will move quickly. But I hope you people are enjoying. I'll finish it in next 20 minutes or so. See, let us discuss the death of a low mass star. So any star can hold its own structure under two forces. The one force is the gravitational force of its own mass, and the other force is the radiative pressure, the radiation emitted by the core. The core, is comprising again the hydrogen, and it converts hydrogen into helium, emitting high energetic gamma rays. These gamma rays are, emitted outwards, and this radiation, apply pressure on the stellar envelope. So this radiation pressure tries to expand the star, and the gravitation of the star itself tries to shrink the star. When these two forces are in balance, the star is in stable condition, like our sun, and like most of the stars, they are spending almost 90% of their lifetime in stable equilibrium condition. But when the core converts all this hydrogen into helium, the fusion process stops or reduces its rate, and in that case, the radiation pressure also reduces, and the gravity takes its toll, and star started shrinking. In this condition, some things occurs in the core. The fusion process suddenly increases, and it throws away almost all envelope. So envelope is, say, 90% radial structure, but remaining 10% structure, the core of the star, converts helium into even heavier element. So helium fusion stars, and it converts into carbon and oxygen, maybe sometime neon and magnesium. But after this carbon, neon, magnesium, if star is small enough in mass, if it has not sufficient mass, the core has not sufficient mass, the further shrinkage of the core and further fusion of the heavy element stops, and then the core becomes white dwarf. It is very hot core, so it emits light in all the wavelengths, so it is white light, and it is very small star. The size of this remnant is barely 1% of the size of the star in radius, or millionth of the size in volume. So it is very tiny, dwarf component. So that's why it is called white dwarf. But what if the star is very massive, very heavy, heavier than 3 times the mass of the sun, like the known star of Betelgeuse in the Orion constellation? In such heavy stars, what happens? Initially, hydrogen fused into helium. Then, with time, helium fused into carbon, oxygen. Those fused into neon, magnesium. Again, fusion goes on to silicon, sulfur, and so on and so on. So you will have an onion-like structure. The outer layer is made up of hydrogen. The inner layer is made up of helium. Fused hydrogen is helium. Then even further layer is made up of carbon, oxygen, and so on and so on. So you have onion-like structure. The last fusion product will be iron. And we know that iron can neither fuse nor you can produce fission process. So this way, iron is the final stable product. But what happens to this iron? Because this iron also has a very high mass. The core of this iron itself is maybe sometimes heavier than sun. In this case, this iron cone collapses. That collapse within a second. Remember, within a second, all this iron core collapse, and it emits energy, huge amount of energy. The energy emitted by this collapsed core is more than the total energy emitted by billions of stars in the same galaxy. So this whole structure goes into outburst, the iron core collapse, but the emitted energy actually throws away all these outer envelopes of heavy elements. And you will have this kind of scenario. So you can see a faint star here in the left image, which is actually a star before this kind of dying process. But when the iron core collapses, it brightens like anything, and this burst is called supernova burst. So supernova burst occurs when a core collapses in a star, and the material thrown away from their collapsed cores, you can see as this beautiful colorful structure. So the heavy material are actually thrown away in the space, and you will have a tiny but extremely dense remnant of the core. If the core has mass below some limit, then the core made up of neutron is called neutron star. So whole core is, converts into the neutron. The whole star or the whole remnant part is made up of neutron, and you will have neutron star. The typical size of the neutron star is smaller than Rajkot or Ahmedabad. Few tens of kilometer is the radius, maybe 10, 12 or 15 kilometer radii of the neutron star. So neutron star is a very compact object, yet it is massive than sun. So they are very dense object. Even spoonful of a neutron star is heavier than Everest mountain. They are very dense. But what happens if the core component is even massive? So in that case, the final collapsed product is basically a black hole. So the neutron star also continues shrinking, and it shrinks to a level such that the escape velocity on its surface will exceed the velocity of light, and it will convert into black hole. So all neutron stars and all black holes are actually remnants of the dead star, and they are made through the process called supernova process. As I told earlier, 90% of the stars are in binary system. So it may happen that the supernova occurred in a binary system, in one of the star of the binary system. The other star is a normal star, but one star, the heavier star, as you know, passed through its death process and converted into black hole. These two stars are very close to each other, and the gravitation of this black hole tries to pull plasma material from this normal star. This plasma forms a disk because of its angular velocity, and eventually accretes onto the black hole. Now we cannot see black hole, but the plasma accreting on the black hole are actually forming this disk. And as plasma moves closer to the black hole in the disk becomes hotter and hotter because the gravitational potential energy releases and makes this hotter. The inner part of disk has temperature millions of Kelvin. Such hot plasma starts emitting high amount of X-rays. See, ordinary stars don't emit very strong X-rays. Yet, if we find some stars, some sources in the space emitting strong X-rays, high amount of X-rays, we can say that there must be a black hole. Just presence of strong X-ray is not sufficient. The spectrum of that X-ray and the spectrum in the other wavelengths like optical and IR light also should follow some kind of pattern. Then only we can say. But this is an indirect method of detecting a black hole. Occasionally students ask me, if we cannot see the black hole, how can we detect it? The reason is this. This is the major method used to detect a black hole. If the black hole is in binary system, the accreted material, shows the presence of that black hole. The black holes can form from the star, and these black holes are called stellar black holes. But there are black holes known in our galaxy and in other galaxies. A group of scientists studied various galaxies and their core, their center, way back in 90s. 1990s, they wanted to discover black hole if they're present in the center. They have selected tens of galaxies, studied these galaxies, and surprisingly, they found black holes in all the galaxies. Black holes are existed in all the galaxies, their core. And these black holes are supermassive black holes. The mass of these black holes are hundreds of million times larger than the, heavier than the mass of the sun. So as I told earlier, there are two types of black holes. One is called stellar mass black hole made from single star, and others are supermassive black hole. The black holes heavier than millions of suns, and these black holes are almost present in all the galaxies. If they are present in other external galaxy, they should present in our own galaxy also. So this is the picture we have formed of our own galaxy, and you can see the core part of the galaxy, which is in Sagittarius constellation. So this is the core part of the central part of the galaxy. I am still zooming in, and somewhere here the actual core of our own Milky Way galaxy lies. These images are actually infrared images. You can see that the core part is actually dark because the galactic plane contains a lot of dust and gas, and this dust and gas scatters the light coming from the inner part of the galaxy. So optical light gets scattered very easily and you cannot see it. But we know that infrared light can pass easily to this scattering, and so, we study the inner part of the galaxies using infrared wavelengths, not in optical wavelengths. So this is the further zoomed part of the actual center of our own galaxy. In this left image, you can see the stars are blurred. This blurring is mainly because of the atmospheric turbulence on the Earth. The atmospheric turbulence blurs the image. But recently, we have developed a technology called adaptive optics, and that compensates the blurring effect by the atmosphere, and you can see a very nice clear image. The small square I have shown here is actually observed in this adaptive system, and you can see the stars are very clear. Two groups by Andre Geis and Einhard Genzel, they have studied independently this extreme central part of our galaxy, and they have not studied once. They are keep observing this central part for years. And I am just moving back and forth, and you can see the same stars are moving. You can see the same stars are moving. And if they are moving, there must be some central force. So these people, these astrophysicists, have from the motion of the star, they have completed their orbit, and they have discovered that all the stars are actually orbiting around a central point of the galaxy. They have tried to find some object in this central point. They could not find the star, anything here. But they found a star called SO2, which is orbiting highly elliptically around this hypothetical center. And in that elliptical orbit, the star comes very close to the center, few astronomical units, almost as close as the Jupiter's orbit, and still this star passed through the center and move ahead. So the star has, passed through the center to this close distance. This shows that the central object, whatever it is there, is smaller than the orbit of the Jupiter. Then only the collision doesn't take place. Also, from estimating the mass of these stars by other means and applying Kepler's law, this scientist estimated the mass of this central object, invisible central object, and they found that the mass of the invisible central object is 400,000 solar mass. So we have an object which is 400,000 times heavier than the sun, yet smaller than the orbit of the Jupiter. It can be nothing else than black hole. So we have indirectly discovered a black hole in our own solar system. Here are the other examples of the black hole in the galaxy, the non-black hole in M87 galaxies. The jets are also coming from these supermassive black holes. I'll not go in detail. And recently we know that we have actually imaged this black hole. Actually, we cannot image the black hole, but we have imaged the shadow and the surrounding of the black hole. We have not imaged in single instance, we have imaged on 5 instances, and the images are consistent, supporting the reality, the real nature of the image. With this, I will quickly move to my third topic, the gravitational waves. So, till 2015-16, we had only one way of studying universe, and that was light. Apart from light, you cannot study the distant stars by other means. Nothing can come from there except cosmic rays, and neither you can go there and change anything. But the gravitational waves are actually the totally different spectrum. With discovery of gravitational waves, we have opened a new window very much parallel to the electromagnetic waves. So by studying these further objects in gravitational waves, we can know the physical processes occurring there, which we cannot know using electromagnetic waves. So this is really a revolutionary discovery. Starting from quick history, Newton, we know that has discovered gravitation, and the story is that he saw an apple falling from an apple tree and he discovered the gravity. It was not like that. Fortunately, he was not sitting below a coconut tree. Otherwise, he would not have, alive to discover the gravity. Actually, Newton was actually kept sitting in an apple tree in a similar situation what we are facing in a pandemic quarantine kind of phase, and he utilized this time, but he actually finalized his theory of gravitation after some tens of years, maybe 18 to 20 years. It was not instantaneous discovery. It took time. Even the scientists like Newton took tens of years to discover these things. So this is the actual real apple tree still preserved in UK, and one branch of this, or rather 2 branches of this tree, was brought by Professor Jayant Narlikar in Pune, in a campus of IUCAA, Inter-University Center for Astronomy and Astrophysics. We know that apple cannot grow in Pune in full-fledged. Still, the tree you can see here is actually the real replica of the original apple tree. Another secret, not universal, but interesting secret. Yes, so Newton told that the gravitation was instantaneous. That means gravitation, effect of gravity moves instantaneously. But it was Einstein who actually explained that no, even the gravity, the gravitational information, the effect of gravitation also moves with the speed of light. That means even if the sun, let us assume, disappears suddenly on a moment, the Earth will still orbiting around the sun for next 499 seconds, because the effect of gravity, the absence of gravity, reaches to the Earth after 499 seconds. And this way, Einstein also predicted the turbulences, the perturbations in the gravity, and he said that the gravitational field also have waves. Now, gravitational waves are, different than the waves we have encountered, like sound waves or water waves. They are actually 4-dimensional waves, the waves in the space and time. So this wave passes in such a way that if they are passing through some material, let us say passing through the earth will shrink in one axis and expand in the perpendicular axis. So it is expansion and perpendicular harmonically in both the axes. Like this picture, you see that if gravitational wave passes through this place, either the picture will expands vertically and shrink horizontally, or it will shrink horizontally and expand vertically. If so, it would be very easy to discover this gravitational wave. But no, it is not. The trick is here. Let us assume some reasonably strong gravitational wave passing through whole Earth, and it shrinks and expands the Earth. Still, the difference in the shrinking and expanding of the Earth is much smaller than the radius of a simple proton. Remember, measuring the Earth and change of its size with the accuracy of 100 to 1000th of a proton radius is very difficult, next to impossible. And it was impossible since few decades back. But we people, I mean scientists, are actually made, they always imagine what apparently impossible to other people. And we have designed a dedicated instrument. This instrument is very similar to the Michelson interferometer, except that in Michelson interferometer, the beam reflects only once from these two mirror arms. Here, we are reflecting them back and forth between these two intermediate stations multiple times, 100 to 1000 times. And then this partially reflective mirror allows the beam to come back, and this beam again interferes here and discovers on the detector. The idea is like that. If the Earth is fully stable, then and you arrange these two beams to cancel out each other in destructive interference, you will never get signal at the detector in these two beams. But let us assume that some gravitational wave passes through the Earth. It will pass through this interferometer also. It will also shrink and expand these two arms in opposite way, and you will have condition away from the complete destructive interference, and you will get some weak signal here. So this is the basic principle. Now, in order to detect tiny amount of displacement, we need to have these arms much larger. And USA have established two observatories, two LIGO, Lesser Interferometer Gravitational Wave Observatory, one at Hanford Observatory in the western bay, and the other in the Livingston in the eastern coast. And these two observatories are like this. This is Livingston, this is Hanford, one is in forest, one is in desert. And they are made up of 4-kilometer arms of the length 4 kilometers. The lesser beams are, reflected from here and there. Now remember, this system will have huge amount of noise from terrestrial sources also. Like the gas within this tunnel itself will, keep scattering this laser and add noise. To avoid that, this 4-kilometer long channel, 4 into 2, 8-kilometer long channel is in complete evacuation. In the evacuation best possible on the Earth for such large volume. So it is very expensive experiment, large structure within complete vacuum, and also very sophisticated instruments used here. I can, talk for whole day on this experiment. It is fantastic, but I will quickly move. This is the inner picture of the central part where the actual interference occurs. And this is the region where the vacuum and within that the optics are there. You can see the optical components. These are the best optics available till date on the earth. These technologies have been developed for this experiment. This is billion-trillion-dollar experiment. And here the quick view. This system can detect the deviation of these length arms from 1,000th of a proton diameter. Very precise system. Now this is not easy. Even if you put all your technology in the system, still you get such kind of a noisy data. Now, dealing with this noisy data is very tricky. Two things you should know. One, you should know what you are looking for in this data. You must know what you are looking for. And second thing, you must know how to look for that. You must know how to reduce the noise and look for what you want to look. So here, the first part, what you are looking. Suppose two black holes are in binary system and they are orbiting around each other. And as they are orbiting around each other, they are emitting gravitational waves. You can see here. And these gravitational waves are emitted, so the energy of the system reduces and the two stars are coming closer and closer. You can see here, earlier, they were emitting gravitational waves at lower frequency, higher wavelength, but as the stars are coming closer and closer, their orbital period reduces, they are moving faster and faster, and eventually, the frequency of gravitational waves also keep increasing. At this point, suddenly these two black holes collide with each other. They simply collide with each other, and this collision produces intense gravitational wave, and that's all. They form a single black hole. These two Indian scientists, remember, not Indian origin, they are still in India, working in Indian institutes. These two scientists contributed significantly in these discoveries, in this signal. This is Professor Bala Iyer working in ICTS India, and he and his team have actually developed mathematical model for binary black hole of different masses, different distances, and different conditions, and they produce the expected signal. So if the system is like this, what kind of signal it will produce? What kind of gravitational signal it will produce? So Professor Bala Iyer and his team told the world that what kind of signal we should look for. And Professor Sanjeev Dhurandhar, working in IUCAA, he is retired now. Both of them actually are retired now, but their team is working across India and across world till then. So Professor Sanjeev Dhurandhar and he's one of the postdoc developed few algorithms to reduce the noise in this noisy data and get the actual signal what we are expecting, signal like this. So both the scientists and their work have been cited in the first discovery paper of the gravitational wave. Their contribution is significant. And one of the student of Professor Sanjeev Dhurandhar, Professor Anand, is working in IIT Gandhinagar. He is faculty in IIT Gandhinagar, continuing his research on gravitational waves. Anand Sengupta. And these are the first signal we have seen of gravitational waves. See, this signal is very noisy. After removing all the noise and all, you got this kind of signal. Remember, if this kind of signal you got on one observatory only, it could be anything. It could be signal from, say, earthquake, or it could be signal from, say accident occurred near the observatory. Even if two cars, collide with each other, say hundreds of kilometers away, the vibrations can be detected in this sensitive instrument. But after removing all the noises on both the observatories, yet we are getting very similar signals in both the observatories, separated by thousands of kilometers. And these signals are very much in line with what we are expecting from a black hole collision. So these are the mathematical model you can see here fitted in the actual observations. And these are their frequency spectrum. You can see that frequency keep increasing and eventually they collide. So two black holes were orbiting around each other. Eventually they collide and form a new black hole. And the gravitational wave emitted by this system was detected by us. And this should be the system. The sizes of the black holes are here. The sizes of the individual component black holes are very much comparable to a single state of an India, and the final black hole is more even larger than the largest state, that is UP. With this, the final remark I will put, this two observatory can actually locate the event in the sky also, but problem is there are only two observatory, so location will be very coarse. If you have three observatory in non-linear configuration, you will have triangular situation, triangular arrangement, and you can locate the position of the event in the sky more precisely. After a lot of discussion with many other research groups worldwide, eventually Indian community won this prize. The third LIGO observatory have started establishing, commissioning somewhere in Maharashtra. A group called LIGO India is working for that. And as I told, the LIGO India will be very similar to the LIGO at Hanford and Livingston. And these observatories need high vacuum also. So the Institute of Plasma Research, IPR, situated between Ahmedabad and Gandhinagar, a team from IPR is also working in LIGO India for this vacuum system development part. Many other institutes and scientists are also working rigorously for LIGO India. And after maybe a few years, LIGO India will also be in working condition, and we will start detecting gravitational waves from our own motherland. With this, I will pause my presentation. I have not kept the slide of thank you because I don't want to stop here. I want you people to continue thinking on this and on other scientific problems. And I want you that if you are really enjoying this journey, the journey of understanding, journey of knowing research is joyful, but journey of, really living in research is even wonderful. अगर आपको उसकी आदत पड़ गई तो वो व्यसन सबसे खराब है. Thank you very much.
Thank you so much, sir. Let us all come back to the Zoom application from the universe. Now, sir, thank you so much for this lecture. We would move towards the question and answer part. There are, I can see so many questions and
Okay.
Let us take the first question from Rahul Dwivedi.
Okay, I'm stop sharing. Yes, Rahul.
Hello.
Yes,
Hello,
Rahul.
good afternoon, sir.
Good afternoon.
Sir, my question is, if we used gravitational waves from single source in Young's double slit experiment, will we detect the interference fringes on the screen?
From the single source, yes. So it's very interesting question. Like supernova outburst, supernova even from a single star will also produce gravitational waves. But these waves and their pattern will be totally different than the pattern I have explained, that is from the binary black hole. So people are actually working on getting the kind of the pattern of the gravitational waves from the single event from the single source. Yes, so our system is still not, capable enough to get these weak signals. Our system can detect only strong signal from merger of binary black hole or even merger of binary neutron star, which is weaker than the black hole merger, but still we can detect it. But yet we are not in position to detect signals from the single source. But I'm hopeful that very soon we will detect signals from the single source. Yeah. Next question.
Yes, sir. Thank you, sir. Now, next question we take from Shubham Sharma.
Yeah. Good afternoon.
Good afternoon, sir.
Yes.
So my question is, all the black holes are having the same atmosphere?
So atmosphere is very tricky to talk about. Actually, we cannot talk about the black hole, the composition of black hole itself. See, black hole is the body which is well below event horizon. So event horizon is kind of a boundary till which our physics works. Within that event horizon, which is called singularity, our non-physics is not applicable there. So we cannot directly apply our physics. Still, we know something about the spin of the black hole and few more things, but otherwise it is next to impossible for us to say and prove anything about the composition, the structure, the atmosphere, and all about the black hole. But yes, the disk around the black hole, the accretion disk, is very similar to the accretion disk in other systems. So accretion disks are very common. Even when star forms, it forms accretion disk. Even binary stars are orbiting around each other, they form accretion disk, and so on. So this accretion disk is common, but it's difficult to say anything about this.
Sir, can black holes change their place?
I think we should move on and
Yes,
take questions from
I'm
others.
sorry, Shubham, we cannot take. Yes, we can take the next question from Surjit Mukherjee, sir. Yes, sir.
Hello.
Yeah,
Hello,
please.
can you hear me?
Yeah, I can hear you, sir.
Yeah, Dr. Joshi, you have given an excellent talk. It's very informative and I have really enjoyed this.
Thank you.
I have just one curiosity. Actually, I am not very expert in this field. That I could not get that how you remove that you can background from the actual signal of gravitational wave.
How can we remove the background? So a lot of technologies have been applied. Like in the observatories, they have applied several earthquake sensors around the observatory. The signals from those sensors are used to remove the signals from the earthquake as well as other kind of collisions. And then, you know, high level of, I would say, complicated algorithms are applied to get signal from the signal. So I would put it this way. Instead of, I would say, removing the signal, I would say detecting the signal, detecting the expected signal.
Okay. Okay. I got it. Yes.
So it is similar to, yeah, you know, this correlation techniques and something like that.
Yeah. Okay. Okay. It is very interesting. Very interesting.
Highly interesting subject. Yes.
Thank you so much. Thank you. Thank
My
you.
pleasure. Yeah.
Yes, we take the next question from Advait Joshi.
Hi, Advait.
Hello, sir. Good afternoon. It was a wonderful lecture. Sir, what is that? How a light has a spectrum. So similarly, can the gravitational wave have its own spectrum?
Yes. So gravitational waves also have a spectrum, and till date we could target only a small part of the spectrum. So yes, gravitational waves also have a wide varieties in the different spectrum, and various phenomena emits gravitational waves in different wavelengths, different frequencies. So yes, so with time, with technology, we will be able to explore more spectral regions of the gravitational wave and get more information from the universe. Thank you.
Yes, sir. We take the next question from Khushi Arora.
Good afternoon, sir.
Good afternoon.
Sir, my question is based on the Big Bang theory. Actually, जब बिग बैंग हुआ था तब एक सिंगुलैरिटी से वो एक्सपैंड हुआ अपने यूनिवर्स, या मानते तो क्या वहां पर एनर्जी कंजर्वेशन लॉ लगता है?
बिग बैंग होने के बाद जो यूनिवर्स बना उसमें एनर्जी कंजर्वेशन लॉ लगता है. बिग बैंग होने से पहले जो था उसके बारे में एज अ फिजिसिस्ट मैं कुछ नहीं बोल सकता.
सर क्या स्ट्रिंग थ्योरी अप्लाई हो सकेगी फिर?
That is beyond my reach, you know, that is beyond my reach. तो ये ऐसी चीज है कि इंडिया का कॉन्स्टिट्यूशन अब दूसरे कंट्री में नहीं चला सकते हैं, है ना. तो ये ऐसी बात है. हमारे पास जो कॉन्स्टिट्यूशन है, हमारे पास जो रूल बुक है, वो हमारे नॉन यूनिवर्स में ही चलती है, क्योंकि हमने वो नॉन यूनिवर्स की फिनोमिना को ही स्टडी करके वो रूल्स डिस्कवर किए हैं. So difficult to say. Next question.
Yes, sir. Very true. Now, now you take the next question from Sagar.
Yeah. Hello, sir.
Hi, Sagar.
Good afternoon. Yeah, my question is that with the help of nanotechnology, can we make such a particle? Means we can say that a condensed particle like 4 or 5 centimeter, which is very heavier.
See, first of all, I am not an expert of nanotechnology, so can't say what kind of densities we can produce using nanotechnology. And many nanotechnology experts are there. Probably you can ask them later on and discuss.
Yeah, actually, I had different question, but this question struck me suddenly. My question was.
I think we should move to other participants. We can
Exactly, sir. Yes, sir. We move towards the next question from Anirudh Singh.
Good afternoon, sir.
Good afternoon, Anil.
Sir, my question is, do gravitational waves also exhibit property that are exhibited by ordinary waves? And if so, then how we can measure them? Strictly, I'm talking about diffraction.
Okay. So theoretically, at least interference definitely occurs. I'm not sure about diffraction, but interference of gravitational waves are always possible. And we have only, discovered the deformation due to gravitational waves. Other properties of gravitational waves have yet been observed. So yes, interference at least is possible. Yeah. Next question. Hello. Am I audible?
Yes, you are
Hello,
audible.
sir.
Yeah, please. We shall move to next question.
Sir, my question is, if we detect any exoplanet, and it has some nomenclature method to name the exoplanet.
Yeah. So as I told, the name of the planet comes from the star. If the star's name is, let us say Pictoris, Alpha Pictoris, so the planets will have Alpha Pictoris B, C, D, A, F, and so on. So simply you put alphabets, small alphabets B, C, D, E, F, G, H, I, J, K, L after the name of the star, and that will be its planet. Now, how can we name the stars? So there are various ways to name a star. In fact, most of the stars have more than one names. See, we have billions of stars, and we cannot study all these stars very individually. So all these stars are studied in group in a survey. So sometimes the star names are given from their location on the stars, their coordinates, or from the least number of their catalog surveys and all. So naming a star is again a challenge in astronomy, not scientific challenge, but yes, pseudo-scientific challenge. So naming the planet has this tradition from the name of the star. Yeah.
Yes, sir. I think that's it for the question and answer session. So now we move towards the last and most important part. We move towards the vote of thanks. For that, I would like to invite Ms. Hardika Goswami, a PhD scholar in our Department of Physics. Welcome, Hardika.
Good afternoon, all.
Good afternoon.
Honorable Vice Chancellor, respected Pro Vice Chancellor, and dignitaries as Dr. Narottam Sahu, Dr. Mehul Rupani, Dr. Girish Bhimani, Professor Mihir Joshi sir, Professor Hiren Joshi sir, and all the participants. It is my privilege to have been asked to propose a vote of thanks on this physics occasion, and on behalf of Bhautiki Yatra, a travel for scientific Indian minds, webinar jointly organized by Department of Physics, Saurashtra University, Rajkot, Department of Science and Technology, Government of Gujarat DST, and Guj Coast and Essence Tech, an entire organizing team. And my own behalf, I extend a very hearty thanks to all, and a big thank you to Dr. Vishal Joshi sir for gracing your important work and sharing with us your findings and opinions today. As astronomy has been always one of the fascinating subject in the physics field and to every physicist. And I must mention my sense of appreciation to sir for giving an excellent coverage to the universal secrets with the knowledgeable and Nobel Prize winning topics like exoplanet formation and detection of exoplanet and also detection and formation of black holes as well the LIGO India and the detection of the gravitational waves, which are the fascinating subjects in the physics field. And as I personally want to tell you, sir, that I met Vishal sir at Guru Sikhar Observatory, Abu, as an amateur astronomer from the Big Bang Astronomy Club, Rajkot. And by giving such an wonderful talk, you have waken up amateur astronomer inside all of us. Thank you very much, sir. And finally, I would like to thank Dr. Professor Nikesh Shah, sir, Dr. Piyush Solanki, Mr. Chintan Panchashra, Mr. Harshal Sanghvi, and all the PhD scholars for their enormous cooperation in the organization of this event, and a warm gratitude towards all the attendees. Thank you very much.
Thank you. I also take this opportunity to thank organizing agencies and organizing people. I'll not name them, but I'm really thankful to giving me an opportunity to interact with me, interacting with all these young ones. Thank you again.
Thank you so much, sir, for joining us, and we are really proud to say that you are the part of our alumni. Thank you so much, sir, for joining. We end this session here, and once again, we will meet tomorrow on the same platform and same time. Thank you all. Have a good day.